Hi, I am Arunabha and this is my final presentation of AMI 56900 Mechanical Behavior of Materials project. So the title of my project was Analysis of Crack Propagation Using Fracture Mechanics. So here, using the principles of fracture mechanics, I can explain like this plot can explain how a crack can propagate, whether a crack will propagate, whether failure will occur in a particular material because of the propagation of crack. So these were the objectives of my project work. First of all, I would like to provide a brief overview of fracture mechanics. I'd like to go over the design of a bimetallic strip which I used in my project work, and then I will be analyzing the design using fracture mechanics principles. I will come to energy release rate calculation, which is one of the most prime factors here in fracture mechanics, and then I will be comparing two types of case studies, one with different mesh sizing and then one with thermal stress. I'll be comparing the results of the two and I will conclude at the end. So what is fracture mechanics? Why fracture mechanics is required? Why do you need to study fracture mechanics? So fracture mechanics is about studying and analyzing materials which are having cracks. It can predict whether a particular material will fail, whether a crack will propagate in a material. It is based on the theory of elasticity and plasticity mainly, specific theory of elasticity. And for prediction of the failure, information is required, like the applied load, the residual stress, the size and location, the origin of the crack, the coordinates of the crack, the shape of the crack. So these are required. So actually in industries nowadays, there are products that are designed which have two materials combined together and bonded together. So using fracture mechanics, we can characterize the strength of those bonds, like how much is the integrity of the bonds. So fracture mechanics comes useful in that. So this was the geometry that I had made for my project. This is a bimetallic strip of aluminium and steel. So here where there are two parts, there should be two nodes, one for aluminium, one for steel. And this edge is being shared by the two materials, aluminium and steel. So this is a common edge. And this are done by using the shear feature called, there is a shear feature in ANSYS space claim design tool. So with that I define this edge. So this is about the geometry of my model. These are the materials that are used in analysis, like structure, steel and aluminium. These are the properties. Specifically density, Young's modulus and Poisson's ratio will be required for further calculation of energy release rates and the relation between energy release rate, stress intensity factor, etc. So I used a 2D analysis, 2D plane stress analysis for my project work. So the mesh was kept as core sizing with the default size. I had not changed the mesh size initially. And for the boundary conditions, I had provided a fixed support at the bottom edge, displacement at the top edge with about 10 millimeters in the y direction. So this was the mesh actually, which I had obtained after designing my model. So this is quite a coarse mesh, as we can see. It's line to line and there should be no issues with this mesh. So this is the mesh of the bimetallic strip. Okay, so this was the boundary condition that I was talking about, a displacement of about 10 millimeters at this edge, and there's a fixed support at this bottom edge which is not shown here, but there's a fixed support here and there is a displacement of 10 millimeters here, and this is actually the crack that has been defined in the middle. So this was like the total deformation, about 17 millimeters after solving the mesh of the default mesh sizing. This is like the maximum at the right edge and the minimum at the bottom left edge. So different viscosity values, we get results at different viscosity values. In ANSYS workbench there is a fracture tool, and with the help of that fracture tool we can calculate the different viscosity values. So using this viscosity values we can find out the energy release rates, how much energy is there at the crack tip, whether the crack will propagate. So viscosity stands for virtual crack closure technique, and this was initially developed actually for calculating energy release rates. Here SIFS stands for the stress intensity factor, It's the intensity of stress at the crack tip actually. And the G1, G2, G3 here refers to the different modes of fracture, mainly the tensile, tearing, sliding, the three modes of fracture mainly. So this is a glimpse of the vicissity values, how we get that on workbench. So vicissity stands for virtual crack closure technique, as I said, and it is used to actually calculate the energy release rate of a cracked body. There are some assumptions that vicissity holds, like crack growth occurs along a predefined crack path. The analysis will be non-transient, it will be quasi-static, that is, it will not vary over time. And the material will be linear elastic, maybe it's isotropic or anisotropic, orthotropic, doesn't matter, but it will be linear elastic. These are some assumptions that vicissity assumes. So this is how the energy release rate is calculated. Vicissity assumes the energy needed to separate a surface is same as the energy needed to close the same surface. This is a very important assumption, and based on this, the calculation of energy release rate occurs. So for a 2D crack geometry, this is the relation of calculating the energy release rate from factors such as delta A, which stands for crack extension or crack length, Ry and Rx. This R is the reaction forces at the nodes, delta V, delta U are the relative displacement between the nodes at the top and bottom surface. We can see the parameters here. Delta U, delta V are the relative displacement between the top and bottom nodes of the crack face in local coordinates x and y. Rx, Ry are the reaction forces of the crack tip node. Delta A, as I said, is the crack extension or crack length. So this, I think, is quite a good representation of the crack geometry. That is, when a crack propagates, it exactly looks like this. At the micro level, we can see that this is the delta V, delta U are the relative displacements. The R is the reaction force. Delta A is the crack extension, like if this is a reference point, how much the crack has extended or how much it has propagated. This can be a good pictorial representation of the 2D crack geometry. So stress intensity factor, as I was saying, the SIFS theorem in workbench was shown is the stress intensity factor. So stress intensity factor is used to estimate the intensity of stress at the tip of a crack. It is denoted by K. And stress intensity factor provides a good criteria for failure, specifically for brittle fracture. But the value of stress intensity factor depends on some factors like geometry, the location, the coordinates of the crack. There is this critical stress intensity factor actually, and it is the value that is required to be reached for the crack to propagate. It is also known as the fracture toughness of the material, and this is the most important factor which governs whether there will be fracture in the material ultimately due to the crack. So critical stress intensity factor is the minimum value of stress intensity factor required to propagate the crack, for the crack to get propagated. It is denoted by K1C, and it is also called as fracture toughness of the material. So these are the different stress intensity factor for different modes of fracture. This is how we calculate the stress intensity factors. So there is some relation for the three modes of fracture, and they are somewhat different just depending on the coordinates. This is the relationship of stress intensity factor to the energy release rate G. Like if you want to find out either one of the two when the other is given and one is not given, and then we can find out with the help of the one that is given and with Poisson's ratio, Young's modulus. So this is the result of the default mesh size. So I had got, after solving the problem, like as I had showed at the beginning, the deformation was about 17 millimeters for the initial mesh size, the default mesh size. The stress intensity factor was about 1.776 times 10 to the power 3 megapascal root millimeter, and these are the vicissity values. It's obvious the G3 is 0 because it's a 2D plane strain analysis, so there will be these two, the G1 and G2 for these two modes of fracture and the combined modes of fracture. So when I changed the mesh size of the crack tip, there are some changes that I could see. Like I set the sphere radius to 0.5 millimeters and the element size to 0.1 millimeter. So I saw that the deformation decreases. So as I decrease this mesh size of the crack tip, there are some changes that can be seen for the deformation. At the initial mesh size it was like 17 millimeters, but now the deformation is about 15 millimeters. The stress intensity factor is increased somewhat. It's about 7.257 now, times 10 to the power 005 megapascal root millimeter, and the viscosity values remains more or less the same, I suppose. So what we can see that these viscosity values are quite useful. Like when there is a stress singularity at the crack tip, we can use these values to rely on and depend and find out. We can compare different designs using these viscosity values, and how we can reduce the energy release rate and avoid things like fracture, delamination, etc. So these data are quite helpful. So this is the total deformation at the changed mesh. That is, when we change the mesh size, it's about 15 millimeters. It is maximum at the right edge. This is when the thermal loading. I provided a temperature of about 100 degrees centigrade, and this is how it occurs. This is how it comes up after solving the deformation. It's about 0.041 millimeter. That's quite less as compared to the static structural displacement, as we can see. So these are the results under thermal stress. The total deformation is much less. The stress intensity factor is much less. It's almost come down to a negative value, and the viscosity values is also decreased. So these are my conclusions, which I can conclude after finishing this project work. Like, on reducing the mesh size of crack tip, the total deformation decreases, but the stress intensity factor increases, and the total energy release rate increases considerably somehow, not much. And the thermal stress deformation is very small. The stress intensity factor reduces almost to a negative value, and the energy release rate also decreases substantially. So using different viscosity values or energy release rate values, we can compare different designs, and we can see how the energy release rate can be minimized. And our objective should be to minimize the viscosity value as much as possible in order to avoid fracture. Okay, so I suppose I've given a quite understandable overview and clear comparison between two different mesh sizes, and how the fracture takes turn when a thermal stress is provided. I hope this is a preliminary but quite a significant description of crack determination of energy release rates, whether crack will grow further using fracture mechanics principles. And this is an elementary or fundamental way of using fracture mechanics in material science or solid mechanics. Thanks.